joining us, and I'll pass over to Kevin.
Great, thanks everybody. So I'm just going to paste a couple of links here in this chat. These are the links that you can see on the agenda there. So there's a registration form most of you have filled out, but if you want to get on our email list, just fill that out real quick. No big deal. And then when you're leaving, feel free to fill out this feedback survey if you have any messages you'd like to share. The basic protocol is we're going to ask that folks mute your microphones unless you're giving the presentation or actively asking a question. And then to ask a question, just type the word question in that chat, and then Adam or I can interrupt the speaker at an opportune moment, and you can unmute and ask your question, or if you just type your question in the chat, we can just read it as well. So that's the basic idea. Let's get it started with Sophia. Sophia Economou is a professor at Virginia Tech. Please take it away.
Can you see my screen?
Yes, we see your full screen.
Okay, great. So if at any time I get choppy, please let me know and I'll switch the video off.
Great,
All
looks
right,
good.
So thank you, Kevin and Adam, for the invitation and for organizing this workshop. And today I'll tell you about our work on efficient ansatze for BQEs. And as the title of the workshop implies, we're at the NISQ era. We know that building a universal quantum computer is a formidable task, and we're very interested to see, can we do something interesting and useful with NISQ devices? And I believe most of us here probably think so. And the problem of many-body physics is a kind of a naturally suited problem to pursue in this realm. And the community is mostly focusing, of course, on hybrid classical quantum algorithms. Since the quantum processors are still at their infancy, we're trying to harness as much out of them and complement them with a hybrid, with the classical computers. So I'll be focusing on quantum simulation. And there's kind of two ways you can view quantum simulation. One is analog simulation, where you create a Hamiltonian in a system, such as called atoms, for example, to mimic a different Hamiltonian. And there, the simulator is controllable. It has tunable parameters. So presumably, you can study various parameter regimes, things like phase transitions, and so on. On the other hand, in a digital quantum simulation, this is more a model that's compatible with the way we think of quantum computing, usually in a circuit model. The evolution is decomposed in a set of elementary gates. And there we want to have good algorithms for refining things like eigenenergies of a many-body system or other quantities of interest. So I'll be focusing on the second paradigm, and specifically on fermionic problems, where you can write down the Hamiltonian as shown here in the first line. I'll try to use that. And we'll be focusing entirely on second quantization, where we have raising and lowering or accretion annihilation operators for the fermions, and Coulomb integrals calculated here classically. And of course, then we need to map the fermionic problem to qubits. So the number of qubits is dictated by the number of orbitals we want to keep from the fermionic side. And I'll be mostly, actually entirely in this talk, focusing on the Jordan-Wigner transformation, where each orbital is mapped onto a qubit in the sense that a zero state of a qubit is an unoccupied orbital and the one is occupied. And as is well known, we need to preserve the fermionic anti-commutation relations, which means that in our quantum processor, our raising lowering operators have to actually be complemented by a string of z's, which will pick up the correct minus sign for occupied orbitals that are come before the one we're raising or lowering. And this naturally leads to multi-qubit gates. Since we have these z strings we're exponentiating, so a gate of this form here needs on the order of n gates. And there have been some really nice recent reviews for mostly chemistry problems, but a lot of these are general principles. So the way variational quantum eigensolver works is you take the quantum processor where you prepare non-trivial quantum states, presumably with quite a bit of entanglement for strongly correlated problems, where you also make measurements of the energy in this case. And then you feed that and variationally change the parameter which enters the state preparation circuit of the ansatz in the classical computer, and from that you can iteratively go back and forth and extract spectra. In this case, they're talking about molecular spectra, but this is a more general idea that can be implemented for solid state systems and so on. And there's been some really nice experiments over the last several years. Here I show some experiments from IBM simulating hydrogen to lithium hydride, beryllium hydride. Similar experiment from the Google group, where they also showed that VQE absorbed certain systematic errors in their circuits due to the variation principle. And there's also been similar experiments from Siddiqui's group. All these are actually from superconducting qubits, because it's a system I'm more familiar with, but similar experiments have been done with trapped ions and other systems. So in my talk, I'll focus a lot on the ansatz part of the VQE, and I'll focus on fermionic problems, but also a few slides in the end on optimization. So a crucial part of a successful VQE is a good ansatz. So the ansatz is prepared by starting from a reference state and applying a quantum circuit on it, which is parametrized through some angles theta, which are given by this vector here. And a good ansatz is critical in the success of a VQE. So the considerations we need to take into account is that quantum coherence is very limited, so we don't want this circuit here to be too long. The classical optimization is also not infinitely powerful, so we don't want to have unnecessarily many variational parameters. And we definitely need to span the space where the solution lives. So ideally, we would have an ansatz that's exact. So here's some of the commonly considered ansatz. One is termed hardware efficient, where basically you use native gates in some alternating fashion. These seem to be highly expressible in the sense that you can create many states span the Hilbert space pretty well. The disadvantage is that if you stop too early, if the circuit is not too deep, it's not guaranteed to be exact. So it's an ad hoc ansatz. It can be inefficient in the sense that you might be spanning too much of the Hilbert space in your attempt to find the solution you're looking for. And there's this issue of baryon plateaus for random circuits. On the more chemistry-inspired side, there's this ansatz called UCCSD, unitary coupled cluster singles and doubles, which is basically the exponentiation of a sum of fermionic terms that contain A dagger A's and A dagger AA. So that's what singles and doubles means. This is inspired from classical chemistry algorithms, where it seems to perform reasonably well. On the other hand, it's not exact. And the main disadvantage is that translating fermionic operators into circuits, gates, is actually not efficient. You get a lot of gates, and the trauterization is not unique. So because we usually stop at finite order, and we've shown that for first order you can get very different results in terms of chemical accuracy. So a point I want to make is that both of these are generic in the sense that they don't know anything about the problem. It's the same ansatz, irrespective of what problem you're addressing. We want to take kind of an orthogonal approach to this, which is coming up with problem-tailored ansatz. And we have two ways of doing this. One is by preserving and imposing symmetries at the circuit level. And the other one is an algorithm we call ADAPT, which I'll talk about in some detail. And the features we're going after here is that we want shallow circuits. We want to have small, if not minimal number of optimization parameters. And we would like our ansatz to be exact in the sense that for some selection of parameters, the ground state or whatever state you're after is exactly given. So in the first approach, the symmetry preserving ansatz, you can view this in a nutshell that you have your whole Hilbert space given by this space here. And then you have some symmetry subspace where your solution lives. So if you know some of the symmetries or all of the symmetries of the state, then you can hopefully incorporate those at the circuit level and not search states that don't have that symmetry. And this can be particle number symmetry, spin symmetry, and so on. So we've done pretty much all the symmetries we could think of. So I'll show you some examples. There's more in this paper than what I can cover. So the first thing we want to do is enforce particle number symmetry. So we are interested in a system with n orbitals. That means n qubits. And then an arbitrary state, of course, is described by these many real parameters. But for a system of m fermions, then the number of parameters we need is actually 2 times n choose m minus 2. So this is a much smaller number than that. And to preserve particle number symmetry, we're in the Jordan-Wigner transform. So we begin by creating a state which has the right number of excitations, so the correct particle number. And then we use these gates that were introduced in this paper in the context of preserving excitations, which contain 2 parameters each. And we have shown that if you create a circuit that looks like this, which only has nearest neighbor interactions, and you separate the circuit this way, then if you apply layers of A gates until you place n choose m A gates, then you can create any state that has a fixed particle number symmetry. Moreover, you can impose time reversal symmetry, which is what you have if there's no magnetic fields, and is common in chemistry problems. So in that case, you further want to set one of these parameters to 0. In fact, it's phi. And we have shown in this paper that you can generate any state in the subspace with 100% fidelity. This is guaranteed to have the minimum number of optimization parameters, and it's actually hardware friendly since I'm only coupling neighboring qubits. This can be easily generalized to spin projection SZ symmetry, where now you encode these as spin up and the rest as spin down, and you essentially use the same circuit. In addition to this, we've also shown how you can impose total spin symmetry, but I'm not going to show it in this talk. So compared to previous works where people try to fix the number of orbitals, our result performs optimally compared to other works so far as we could tell, based on a literature search. And we have also done some simulations where we included noise, and we saw how our circuits work, and they seem to work pretty well. In this case, we're simulating hydrogen 2 using Qiskit, and we're comparing it to other built-in kind of hardware-friendly circuits in Qiskit. And in this case, the number of parameters is the smallest because that's by construction of our circuits. In this case, it so happens that also we have the smallest number of C-naughts, but in general, that's not guaranteed. So many more details about this are given in these 2 papers. So now we can ask, what if we don't know the symmetries of the problem, or what if we want to tailor our ansatz even more to the problem? So another approach is to kind of go even further on this axis of how much you want to tailor your ansatz to the problem. On the one end, you have these ad hoc ansatze, which are the same for any problem you're solving. Somewhere in the middle, you could view the symmetry preserving ansatz I just presented, and then further in the tailoring kind of axis is this algorithm adapt. And I'll show you in the next slide what this algorithm does. But the main idea is that it allows the simulated system to dictate its own ansatz. And by construction, it's a very compact ansatz grown 1 operator at a time. And we use a pool of operators, which we call A. And they're anti-Hermitian, so if I exponentiate them, I get a unitary. And I have my variational parameter theta here. So this is an overview of the algorithm. So you start off with this operator pool and with some reference state, and you want to grow that reference state iteratively. So the first question is, which of these operators do I want to apply to my ansatz to start growing it? And we determine that by measuring the gradient of the mean energy, of the mean value of the energy, with respect to the variational parameter of each, and that gives us this commutator. So you could view this as a measurement, as a new Hamiltonian being generated here, and viewing this as a measurement of some new effective Hamiltonian, one generated from each operator. If that's the ground state, then you're done. So you select, if not, which is typically not the case, you select the operator with the largest gradient, you apply to your ansatz, and you optimize. And you re-optimize all the previous parameters as well at that step. And then you just keep going. Without throwing out the operator that you just used, you put it back in your pool, and then you repeat this procedure, and you pick the next operator and so on. And we call this adaptive derivative assembled problem-tailored VQE. One point I'd like to make is that this stage here is parallelizable. So you could run each of these on a different quantum processor if you like. So the overhead that this gives is actually not too high, and I'll talk more about that in a few slides.
Hey, Sophia, I'm sorry to interrupt.
Sure.
It's like a few people aren't able to see your presentation. I'm wondering if you could try unsharing and resharing just to see if that'll help.
Sure.
Other than that, I have no idea, but worth a shot. Thank you. Yeah, perfect. Okay, I see your screen again. No, okay, it's not working for a couple people, but let's soldier on. Sorry to those others, but we do have a recording, so anyway.
All right. So yeah, so another point I'd like to make before I show you results from this is that in reality, we'll never converge exactly to zero. So we should have some kind of criterion here about what convergence means. And typically what we do is we say if the gradient vector is smaller than some number, then we stop. But you could adjust that criterion with others. All right, so an important part of this algorithm is this operator pool that you choose. And a very reasonable question you might have is how should it be chosen? And how do different pools perform? So I'll start actually with the second question, and I'll go back to the first. So the first time we did this, we came up with this idea. We thought the most kind of natural thing to do is start with fermionic pool, because that's what the UCCSD ansatz contains. So we just took fermionic operators, translated them into qubit operators through Jordan-Wigner, and used that as our pool. So here we simulated, this is all classical simulations I'll show for the remainder of the talk. So we're simulating how the quantum processor performs in the absence of noise classically. So here what we plot is for 3 different choice of molecules. This is a hydrogen chain. These are known to be strongly correlated in chemistry. So they're typically used to benchmark algorithms. We plot the energy as a function of the interatomic distance. And in this scale, the different choices of adapt, so this is different convergence criteria, as well as the UCCSD look very similar because it's a kind of a very broad scale. So we're going to zoom in by looking at the error instead. So this is the error from the exact solution as, again, a function of the interatomic distance. So you see that Hartree-Fock does not do well, as this is expected. The shaded area is what's called chemical accuracy, which is where chemists kind of aim to be in terms of how accurate the solution is. And the orange line is UCCSD. The colored lines, these 3 are different levels of adapt. So you see that the 2 E2 and E3, epsilon 2 and epsilon 3 do better than UCCSD. And you could ask at what expense. So what we looked at here is the number of variational parameters. UCCSD is a fixed ansatz, so it's just a flat line. In the case of adapt, since it's an iterative adaptive algorithm, the number of parameters changes at different, different interatomic distances. So you see that adapt consistently does actually better than UCCSD, at least if I improve the accuracy. And it does so with a much smaller number of variational parameters. In one case where adapt has more variational parameters of UCCSD is exactly the case where UCCSD does not hit chemical accuracy. So at this point, you could ask, is this improvement you see over UCCSD something inherent in the algorithm, or is it an artifact of essentially trotterizing, right? Of taking something that has singles and doubles and writing them as a product, in which case if I reassemble them, I would generate higher terms. And here we show that that's not the case. So if I compare adapt to just picking random orderings in this product, you see that adapt does dramatically better, qualitatively better than various other orderings you can think of, like random orderings or lexical orderings and so on. All right, so so far we used fermionic operators for our pool. These, you have to pay the price that they give long multi-qubit gates, so they might have small number of variational parameters, but you might be paying a high price of C naught. So what we want to do is use a more hardware-friendly pool, and we call this qubit adapt VQE. So here we consider operators that have the form exponentiation of a Pauli operator, and we stop at 4 Pauli, tensor 4 Pauli. So here are some results. So here we compare the convergence, the difference from the exact solution, as a function of the adapt iteration step. And actually, the fermionic does better, that's the red. So the fermionic needs fewer parameters, which is not too surprising because it's, in some sense, it combines a lot of gates with one single parameter. So now I can ask, in terms of a more meaningful currency, which is the number of C naughts, how do the two compare? And if I make that my criterion, then I see that qubit adapt does actually much, much better. So it cuts down the number of C naughts by, in some cases, almost an order of magnitude or more. And we also transpiled fermionic adapt to give it a bit of an edge. And the conclusion is still that this pool does much better. The next thing you could ask is how big should this operator pool be? So here we chose all the strings to begin with, all the Pauli operators that give me a non-zero gradient. And that's a huge number. So I would have to make many measurements to decide every time which operator to add. So what we tried first is just randomly start reducing it and see if the algorithm still converges. And we consistently found that up to a point it did well, but then if I chopped it too much, it wouldn't work so well. And that kind of naturally brings in the concept of complete pools. So we define complete pools the following way. So A's are pool operators. We could reassemble them in this way using identities for these exponentiated operators, where B now is all the commutators of A's with each other and commutators of A's with their commutators and so on until you run out of new operators. And we say that we have a complete pool and qubit adapt can converge when states BI applied to some psi where psi is some arbitrary states form a complete basis. So basically this says I need to be able to span the whole space. And we can numerically verify that this works. So if I pick complete pools according to this criteria, which is the blue, we see it seems to always converge. If I pick incomplete pools, we don't converge. And of course, we want to have small number of operators in our pool because for every new operator we add, that adds a measurement at every stage of adapt. So what we want to show is that what is the minimal number of operators I can get away with and still have a complete pool. So minimal complete pools are defined that way. It's the smallest sized complete pools. And we have shown that the size of complete pools is actually linear, not just polynomial in the number of qubits. So it goes like 2n minus 2. And I'm not going to go through the proof, but I just want to show you two examples of complete pools. In this example, you see that the operators are actually nearest neighbor operators. So they should be hardware friendly. And for 3 qubits, I just have an example of a minimal complete pool here. And there's a long proof that based on induction in this preprint. All right, so in the last two, three slides, I want to show you how some of these concepts apply to optimization problems. So optimization problems can be, it's well known that can be encoded in Ising Hamiltonians, meaning diagonal many-body Hamiltonians. And the solution is encoded in the ground state. And in this case, the solution is separable, of course, because it's a classical problem. And a well-known example is a max cut, where you want to take a cut. So you want a cut that is the largest possible cut for this graph. And you have a weighted version of this, where now you multiply the edges by weights, as shown here. And this is mapped to this particular Ising Hamiltonian. A well-known algorithm by Farhi and collaborators is the QAOA, which is an approximate optimization algorithm, where you start from some initial state where all the qubits are in state plus, and then you apply the problem Hamiltonian exponentiated with some parameter, and this mixer here, this exponentiated Hamiltonian with some other parameter, and you just alternate the two. So this is a fixed ansatz, but it has different possible depths. And as I mentioned, this is called the mixer. So what we wanted to see is, can we use adapt to actually improve in the performance of QAOA? So what we did in this work, we preserved the structure of QAOA. So we have an alternative structure where the problem Hamiltonian appears exponentiated every other operator. But the mixer is actually chosen out of a pool. It's not fixed beforehand. And we tested two different pools, single qubit pools, and pools that contain entangling operators. And here's my last slide with results. So for the max cut Hamiltonian, we show here the QAOA. This is energy logarithmic scale as a function of the layer. So this is the original QAOA ansatz. The orange is with a single qubit pool, and the green is actually if you have the multi-qubit pool. So you see that this does dramatically better than QAOA when you allow the adapt criteria to determine the mixer, and you allow for an entangling pool. Here you could ask, what happens though in terms of C0, since my entangling pool obviously contains C0, then maybe I have to pay that price. But actually we see that the case is actually the opposite. So the adapt multi-qubit pool not only reduces the number of optimization parameters, it also reduces the number of C0s compared to regular QAOA and the single qubit pool shown here. So this is the performance for two different graphs with 6 vertices. All right, so to summarize, I talked to you about ansatze for VQE problems, symmetry preserving circuits, adapt VQE and adapt QAOA. And I'd like to just put up a slide with my collaborators and especially the people from my group who did this work. And thank you for your attention.
Great, thanks a lot, Sophia. Let's see, we have a couple minutes for questions while Tom, if you can get ready with your slides as well. Any questions? I could have one just to get us started, Sophia. So you were using C0 counts a lot. I'm wondering if you had access to other 2-qubit gates, what would be the one that would most efficiently let you make the circuits as shallow as possible, and how much does that matter to you?
That's a good question. So actually, in the first case of the symmetry, I don't know, can you still see my screen? In this case here, where you impose particle number symmetry or spin projection symmetry, actually gates of the type control root, square root swap would be better. Since these are, the native gates in some systems, you would cut by roughly a factor of 3 the C0s. So these actually would be much better for systems where you use tuning, such as I believe in the Google group and other groups, to do the 2-qubit gates.
And is it or is it being able to tune that angle?
Yes, you want to tune the theta.
Okay, great. More questions? Do you see this question in the chat, Sophia, from Kostya? is there an intuition for the factor of 2?
Oh yeah. So that's just because we're looking at complex numbers, and we're just subtracting 2 for normalization and the global phase. That's all it is. Oh, sorry. Are you talking about? Sorry. I misunderstood your question. You're asking about the. Not really. So he's asking about the minimal complete pools here. No, we don't really have an intuition at this point.
Just to butt in, sorry. Like, I've stolen the screen sharing. You might want to reshare if you want to show everybody else a specific slide. Sorry about that.
I think it's okay. I can just mention that Konstantin is asking about the factor of 2 in the 2n minus 2 size of the minimal complete pools. I think this is a very new result over the last few weeks. So we're still learning and building intuition on that. So yeah, at this point, no.
Cool. And we all can love linear scaling. So that's very nice. Thanks a lot, Sophia. I think we'll move on to our next talk from Tom O'Brien, who's a researcher at Google. And I see your slides up here. A minor programming note, I guess Google Meet is being a little inconsistent where some people can't see the slides sometimes. I think our best bet is for everybody to try using Chrome. But other than that, I don't have any other suggestions, unfortunately.
Yeah, so can everyone see my slides? Well, can someone see my slides? That's probably the best. That's probably all you can hope for. I was having issues with Sophia, with seeing Sophia's slides. So I think I don't know what the problem is, but let's see how it goes. Anyway, yeah. So as Kevin mentioned, I'm joined Google this year. Before then, I was in Leiden, and when I was asked to give this talk, I jumped on the opportunity to present some work that was done over a year and a bit while I was in the Netherlands. That I've never been able to. I've just never given a talk at a conference about it before. So this is kind of nice. So the work's probably I think it's the simplest form of error mitigation you can get. So I guess a nice way to bridge from Sophia's discussion of the variational quantum eigensolvers and into later talks on maybe more detailed and intricate methods. We call it symmetry verification. I don't think that name's particularly stuck, but it's the title I've given to the talk. The work I want to give some credit to the Xavier Benet Monroe, because the PhD student of mine who did the theory work, and Ramirez Agastizabal, who's the experimentalist in the lab of Leo DiCarlo, who ran the experiments I'm going to show. So yeah, just really briefly, I'll give some background to this, go over the circuits for direct measurement of symmetries and how you can use this to correct your quantum algorithm. Then I'll go over probably the one key thing to take out of the talk, which is how you can do this error mitigation without using any additional circuitry on your device, which I think is kind of critical for error mitigation, or for NISQ devices in general, right? We don't want the problem to be worse than we don't want the cure to be worse than the problem. And I'll show the experiment and finish up. So let's get into it. So I think most people who go through an undergraduate degree in physics or elsewhere get some notion of the word symmetry and what it means. But everyone likes to be told what they already know. So let me start by going over the basics. If I have a symmetry, if I have a system, usually I describe this with a Hamiltonian H. And a symmetry is just any operator that commutes with the Hamiltonian. Typically, though, we like these symmetries to correspond to have two things. Firstly, they often correspond to some real physical symmetry of the system, like a rotation or a translation, etc. And the other thing is that we typically want them to be really, really high-dimensional Hilbert, have really large dimensional eigenspaces. And the reason for that is that I can choose my eigenstates for H to be simultaneous eigenstates of S. So if I have large eigenstates of my Hamiltonian, then I can I know I can choose them such that they're sitting within this eigenspace, and I can do my entire quantum. If I can do my entire quantum algorithm within this eigenspace, and I know that I know that one fact about the state that I'm preparing, which is it is an eigenstate of S with a fixed eigenvalue. And so, for instance, the symmetry preserving VQEs that Sophia mentioned in her talk is an example of a class of algorithms that would do this. Now, and the crucial part is that a unitary that commutes with any unitary that commutes with the symmetry will preserve this, and I can every time I measure S, my symmetry, as long as I haven't shifted out of that eigenspace, then I do nothing to the state. So I can kind of measure this for free, and if I had a perfect quantum computer, you might just ask, why on earth would I even care about this? Well, we're in NISQ, we don't have perfect quantum computers, and so the idea is that we can use this to detect when something's gone wrong, and the unitary that we actually implemented is not the thing that we thought we had. Now, this is like the idea that stretches back 20 years from quantum error correction and the stabilizer formalism of Dan Gottesman. And the idea is roughly that if I design a large code so that I have many of these symmetries, well, stabilizers in this case, that all that anti-commute with kind of all local, that some of which anti-commute with all local observables, then I can protect myself against local errors by means of detecting them and eventually correcting them. Now, designing such a code, all the codes that we know that are efficient can require an awful amount of extra qubits and an awful amount of extra measurement. And so, by definition of being in NISQ, we're not in the fault tolerant era, and the correction is and doing quantum error correction is currently a bit too costly. But this is like the simplest, the simplest error mitigation version of this. I perform a noisy unitary. I verify that my state remains symmetric under all my available symmetries, and when it's not, I just throw it away. I don't try to correct anything. Okay, so how might you do this? And just to give like a brief, like the circuit design of this, the idea is, I run my unitary, so this would be a VQE, for instance. I then do this measurement circuit, which measures S, returns SI. Now I know I have rho I, unless some measurement occurred in like the last part of the circuit. And then I can take this and I can measure my expectation value, my Hamiltonian, get my energy, optimize my VQE, yada, yada, yada. So you've got a lot of freedom in designing this measurement circuit. I'm not going to talk about the unitary. This is for you to provide. But the measurement circuit is something I'm kind of interested in. And so if you want to take I want to pull out your favorite quantum error correction stabilizers and how you might measure these, you would typically, these S's, I should say, should be Pauli operators. So they, tensor products of X, Y, and Z on the on all of your qubits. And you can measure this quite simply by doing a pre-rotation on all of your qubits, C-naughting them with a control qubit and reading and using this thing to read out the final result. That's kind of great. And from quantum error correction perspective, this is nice because you keep local errors local and you don't propagate anything onto the device. But this is kind of a long circuit. It's order n depth. And so this is a lot of overhead to throw onto the end of your experiment. Now, the first thing we realize is we can do better than this because we can get rid of this additional qubit requirement and just encode the measurement onto one of the qubits that's already in the system by taking these C-naughts and just passing basically you pass the Pauli basis that's sitting on this qubit here down from qubit 0 to qubit 1, and then you pass the combined Pauli basis from these two down to qubit 2, and et cetera, et cetera. You can check that this will actually measure this symmetry in as much as the first one will. But then we found out we could do even better. And I think this is like if you want to take any one thing away from this talk, it's this one. So the idea is that we want to do measurement of a symmetry that will take our erroneous, error-prone density matrix, rho error, and it'll project it to some rho true, which it might contain errors, but at least it's sitting within the correct Hilbert space that we want, like the symmetry conserving subspace. And so then, once what I want to do with this rho true, if I'm doing a VQE or for honestly most other algorithms that I'm interested in, many other algorithms I'm interested in, is I want to try to like trace out the rho true with some operator and get the expectation value of the operator, and then I'll optimize on that. Okay, now let me just, for the sake of simplicity, assume that I have a Pauli symmetry with which I'm going to write in terms of these two projection operators, and assume that I'm targeting the +1 subspace. Right, and so this means that by definition from the previous slide, the +1 subspace is the subspace where, this means that the true density matrix can be written in this form here, right? This is just the Born update rule. If I measure my symmetry and I see that the measurement result was +1, then I will be in this state. And then what you can do is you can do a cute trick. You can rewrite this projection operator in the form 1 + s divided by 2. And you can substitute this line into the equation above and this equation into the original definition of the expectation value. And we see that we have a form for the expectation operator, which is written only in terms of expectation values of multiple operators now, but they're expectation values of operators on the noisy state. Okay. Now this is now something, is assuming O is like a Pauli operator or a linear combination of Pauli operators, which every operator actually is. I can extract these expectation values by just doing single qubit rotations and measurement at the end. And single qubit rotations in NISQ are relatively nice. These are, I want to say, like, single qubit rotation and measurement is about as cheap as you can get for any error mitigation circuit. So this is a nice result. It means that you can project yourself into, you can get the expectation value of the projection of your density matrix into your symmetry conserving subspace without ever having to do it, and without ever having to worry about whether or not you are actually measuring the symmetry that you care about when you're getting readout from your device, as other protocols have done. And so Javi took this and ran with, you know, to check how well it performs. Here is a plot of the bond association curve of H2. So this is, like, you know, the simplest toy model for quantum chemistry that everyone knows and at this point is probably completely sick of. And so you see here basically, you know, the VQEs work quite well in superconducting qubits these days, this is a simulation of superconducting qubits with, I believe, T1 and T2 noise on it. And, you know, so because these qubits are quite good, then most of the points fall almost directly on the line, but we can look at the error in the curves, and you see what happens is we go from just the free VQE with no verification on top of that to the 3 different forms of verification. And you can see that as we go from using an ancilla to doing everything in line, all the way down to the ancilla free, no extra circuitry required result, we go up to about an order of magnitude improvement. And this is, you know, this is what you might expect. The remaining errors here are really the errors that have occurred in the circuit that have kept the state within the symmetry conserving subspace. I can't correct that because it doesn't anti-commute with my symmetry. I should also point out here that once we found this and thought we were very clever, and then we realized that this is effectively an equivalent to the quantum subspace expansion, but taking a different type of excitation operator. And the quantum subspace expansion usually take linear response, linear response excitations. And so here you'd want to do exactly the same kind of theory, but you need to throw your symmetry operator on top of that. And so that's nice. And then basically we took it, and Ramiro ran with it, grabbed it, threw it in a fridge, and gave it a whirl. And these are the results that he got in the experiment. And I think the first thing you'll see, so, you know, the curve on the left is just to, you know, repeat the curve from the previous slide. The curve on the right is the error plot. Maybe it's a bit hard to read. I think the numbers you can see on the left-hand side, you might notice that these are about a factor of 5 or so higher than what we predicted in the theory. That's unfortunate. It's because our error models weren't as accurate as we'd expected. And so Javi took it on himself to try to improve the error budgeting by adding in extra effects until we kind of, you know, like we got as close to the device as we thought we realistically could. So he added in residual so we started with T1 and T2, and he added in residual excitations, error on the optimizer, and sorry, this is like the 2-qubit, like a fairly accurate 2-qubit noise model built off, an accurate model of the 2-qubit like ISWAP light gate that was being done in the experiment. And I guess the key takeaway from this is firstly to say, like, firstly to say that this is showing that we are doing kind of exactly what we expect, because the residual excitations in the T1, this yellow curve and this purple curve, are precisely the things that we would expect the verification protocol to get rid of, because we're verifying here on a symmetry which is like ZZ on the 2 qubits. And these are the X and Y operators. These are X and Y errors, so they're the ones that will anti-commute with your symmetry. The other thing I should point out is to note that this kind of error budgeting is really useful for an experiment, because we realized after this is, you know, obviously we did the simulations after we had the experimental data, and upon finishing, we realized that a lot of the error here was in the optimizer because we had optimized on the raw data rather than the verified data, and so we could probably in future experiments could save ourselves a fair amount of error by not doing that, basically. So that's about it.
To jump in here. I think you're close to the end here. I just wanted to ask to have the next minute or two.
Yeah, sure. I think I'm close to the end. So some notes for future experiment design is that you can improve your circuit to become, I want to say, more resilient to errors by designing in additional symmetries to that. There's an example of doing this for H2 in the paper. And to conclude, I think this is a nice result because it's really low cost, basically. It's about as simple as you can go. And then we got it even simpler than that by just getting everything done in post processing rather than having to add any extra circuits to the device. It's nice, it's simple, it works. Thanks for your time.
Great, thank you very much, Tom. We have time for a quick question. Anybody? Meanwhile, if Lukasz wants to go. Okay, yes, we have one from Philippe. Do you see this in the chat, Tom?
Compares to results when one is tapering. Unfortunately, I don't. Sorry. We've tried. I know that they've tried in Delft comparing this to some other forms of error mitigation, but I think right now the jury's still out in terms of. I guess it's an implementation thing, right? Like the jury's still a bit out in terms of how you should optimize some of these other methods and get them to work.
Very cool.
Sorry,
thank you very much.
Yep. All right,
it's great to see these results. Lukasz, if you could pull up your slides, please.
Yep.
And then we can do a quick poll to see if everybody can see them.
Okay.
Let's see. I do see them.
Can you see my slides? Can you hear me?
Yeah, it looks good to me. Okay, great.
All right.
Please go ahead. I'd like to introduce Lukasz, who's a scientist at Los Alamos National Lab. Please take it away.
Yeah, welcome everyone. First of all, I would like to thank Kevin and Adam for organizing this workshop and for having me here. So I'll be talking about machine learning of noise-resilient quantum circuit, and the work is done together with Patrick Coles at Los Alamos, Mohan Sarovar, and Kenny Rodinger at Sandia National Lab. So here's a plan for the next 10 or 15 minutes. After a short introduction, I will introduce the idea of task-oriented programming and its extension to noise-aware machine learning of quantum circuits. I will illustrate those ideas on two examples. We will use this machinery to rediscover, if you want, two algorithms, one to compute state overlap between two quantum states, and the other one to perform quantum Fourier transform. So I think I don't have to convince anyone that finding quantum algorithms is a very challenging task. However, what's even harder is to tailor a given quantum algorithm to a specific quantum device, taking into account its specific noise and specific deficiencies. Like, for example, quantum computers are usually not fully connected. So when we are thinking about running the most efficient algorithm on a particular device, we have to take this into account. Those devices are also inhomogeneous, so some qubits are better than the others. Of course, there are gate errors, idle errors, and so on. So basically, there are two approaches to achieve that goal. One is to take an exact algorithm and simply compile it to a specific device. So compile gates that are not present in your alphabet, take into account connectivity issues, maybe shuffling things around to account for bad qubits, and so on. However, there is another approach, which is just teach machine learning about the noise of your specific machine and let it find the best algorithm from scratch. And as you can guess, this is the approach that I'll concentrate on today. So here's our framework of noise-aware machine learning, and it contains of those three things. There's a task, there's a training set, and there is a cost function. Let me give you an example of that, and that's going to be computing an overlap between two quantum states, rho and sigma. In this case, our task is to compute that number that you see here, which is an overlap between two quantum states. So that's our task, and that's in the spirit of task-oriented programming. We don't want to give any further information to the machine learning, right? Just that's your task, and come up with the best algorithm that you can for this particular task. So once we identify the task, then we construct a training set, which is just an example of this particular calculation. So here this training set is a collection of pair of states, rho j and sigma j, and their exact overlap, right? Finally, we define a cost function, which measures the distance between the exact outcome, which in this case is this trace between two quantum states, and whatever the algorithm is returning at a particular iteration, right? So now all we need to do in order to discover an algorithm is to minimize the cost function, right? So if I didn't have a noise, once the cost function reaches 0, then I can say that my algorithm works for every single element of the training set. And once the training set is sufficiently large, then I can argue that my algorithm should perform well on other states as well. So that's the general framework. Keep in mind that we want to discover an algorithm for a particular device that is noisy. And the way to do it is simply come up with an error model for this particular noisy device. And every time we compute the cost function, we do it on a noisy simulator that was built using this particular noise model. So that's it, right? For a given task, I construct the training set, and then I minimize the cost function as much as I can. It's very easy to state, right? But the difficulty is in the optimization. So keep in mind that we are optimizing in the space of all algorithms, right? So it's not necessarily like VQE style that you only have some continuous parameters that you are varying to find the minimum of a cost function. Here we want to optimize all the structure of the algorithm as well. And this is what makes it harder. However, let me skip those details. I'm happy to discuss this offline or maybe later. But the message here is that we are optimizing this cost function and evaluating it in a noisy simulator. I will be targeting IBM ORANS. So that's this 5-qubit quantum machine that is schematically shown here. We have those 5 qubits with this particular connectivity, right? Because I'm working with IBM device, this is my basis gate set, right? These are my building blocks that I'm working with. It's pulse, which is pi/2 rotation around X. I have a C0, and I have a Z rotation. So the only variational parameter, or the only continuous parameter sits here in this Z rotation, right? So what we are doing, we are first constructing the noise model of this particular device. So we measure the process matrices for every element or for every building block. So now instead of a C0, I have some process matrix that is similar to a C0, but there is some significant noise associated to it. There are 2 important things here. One is that Z rotation is not noisy. This is the only noiseless gate that we have, because this gate is done in a software stack. So it's safe to assume that this is exact and also instant. However, identity, we assume here that it is noisy as well. And you can check for yourself that when you do nothing, or when qubit is waiting for another operation, it accumulates actually quite a lot of noise. And this is an important thing to take into account. So if you look at this process matrix for the identity, it is quite far from the identity, actually. So we are taking this into account as well. And as you will see, this is an important thing to consider. So let me now describe those 2 examples. So the first one is to compute the overlap between 2 quantum states, right? So the algorithm for that, or a textbook algorithm, is very simple and is well known. It's just that what I'm showing you here. However, this algorithm is difficult to implement because of this control swap gate that you see here. It's just not native to the machine that I'm working with. So I have to compile it, or I have to decompose it first. So here I'm using the something that is known to be the most efficient decomposition of a control swap. It takes that many C0s. Actually, it takes more, but I already simplified things a little bit. However, that's not the end of the compilation, right? We have to take into account the lack of connectivity, right? So not all the qubits are connected. So some of the C0s, need to be decomposed further, and this is what I'm doing here. So here at the bottom, you can see a final version that indeed could be run on a quantum, on this particular quantum computer. And this is some, let me call it manual compilation or human compilation. This is something that everyone can do, or a simple computer algorithm would come up with, right? Nothing too fancy here. All right, so as you can see, this algorithm is fairly sparse in a sense that there is a lot of idling. And as I told you before, this is something that will introduce a significant amount of noise. It also contains a lot of C-nodes, right, which are very noisy. So we don't expect this algorithm to perform very well, as you will see later. This is a result of running a standard machine learning for this particular task for computing state overlap. That was back in 2018. We were looking at some automated ways of finding quantum algorithms. So that was our first approach. I call it standard because it's not noise aware. It doesn't know about any noise properties, of those gates or of the idling itself. It is just trying to find as short algorithm as possible. So we see, indeed, it is shorter. However, because the machine learning was not informed about the noise, right? In a sense, it is still sparse. So noise-aware machine learning can fix that, as you can see. So if we take noise into account, now the algorithm is much more compact, right? It's just very few idle gates. So that's optimal from that point of view. Machine learning found a solution that is using only few C-nodes, and that's good because C-nodes are very noisy gates. However, what's interesting is the fact that it was not minimizing, or the solution does not minimize the total number of gates. So as you see, this machine learning procedure kind of figure out, right, that is better to do something as opposed to waiting. Right, so that's an interesting phenomena that was emergent, right? It just, so happens to be true with this particular noise model because the identity is actually so noisy. All right, so let me now compare those algorithms. So for that, I randomly selected 1,000 random pairs of states, and I measure the error as shown. And first, this blue dots or this blue line is the error of a textbook algorithm. So as you can see, for most of this 1,000 state is pretty bad. And the standard machine learning, so we without noise consideration is already doing better, but we can outperform this with our noise machine learning, which is a significant improvement as compared with a textbook algorithm and also as compared to the standard machine learning approach. Finally, let me go over another example, which is this quantum Fourier transform. Again, the textbook algorithm is well known, right? It's just that. However, again, we have to decompose it. There are no control rotation on your device. It's not fully connected. So, when you take everything into account, again, you find an algorithm that contains a significant number of noisy C-nodes, and it's very sparse, right? There are just this 18 idle gates. Our noise-aware machine learning, again, found a solution that is much more compact, and it just looks better, right, when you look at it. So there are just a few C-nodes, right? There are many those theta angles. So this theta represents Z rotation. So, because it is free, it is noiseless, right? So then machine learning decides, to put it almost everywhere possible, and then it's just optimizing over those gates as well, right? So finally, I'm showing a comparison here between those two algorithms. So again, I randomly selected 1,000 random states, and I'm looking at the error between an exact Fourier transform and whatever the algorithm return for a given input state. And the textbook algorithm performs fairly poorly, right? The error is pretty big, and our noise-aware machine learning found a much better solution. So now for every single state, for every single input state, the algorithm performs much better, up to 2.5 reduction of error. So as a summary, if there is one thing that you should take from this is not yet another compiler, right? We don't need to start with an exact circuit and then later we try to simplify it. Instead, we just start from random configuration, random gates, and we are evolving that configuration, or we are evolving that circuit until the algorithm does exactly what we want, right? And as we saw, there is substantial noise reduction. With that, I thank you for your attention, and I welcome questions.
Great, thank you very much, Lukasz. We have time for a question or two. Feel free to hop in. Yeah, Travis.
Can you read the question for me? I'm somehow lost this chat.
Sure. Thank you, Lukasz. This was a very good talk. I was wondering if in your results you looked at comparing a noise-aware compilation of the textbook algorithm, because that would seem to probably simplify the circuit even more in the face of noise and make it a little bit more resilient.
I don't think so. Well, so
okay.
What we found is that when you don't initialize your algorithm, you are not biasing this probably towards the wrong solution. Well, wrong meaning less optimal than the best one. So we found that the best way is to remove any bias and just let it evolve multiple times and find something that is very different. And this is what happened with this trace algorithm, right? So I told you that I used the most optimal decomposition of control swap. So how come I can find anything better? Well, the answer is, well, do something else. And this machine learning found this something else, which is way more efficient. And we tried to open up this this black box of machine learning, and we eventually figured out what this something better is. Yeah, you can look it up in the paper.
Okay, thank you.
Yeah, this is very interesting. Lukasz, I wonder, has the paper come out on arXiv yet?
As you can see, there are those 5 X's here. So,
right.
It's like every day now. So I put the 6 here. So it's this month, right? Yeah, it should be available. So, if I have an update, I will let you know definitely.
I'm sure we'll all be on the lookout for it. This is very exciting. I think we'll hold the remaining discussion on this. There are some more questions, but we'll hold it for the break, if that's okay, and move on to Mohammad. So Mohammad, if you could please bring up your slides. Mohammad Hafezi is a professor at the University of Maryland, and please take it away.
Thank you. Thanks, Adam and Kevin, for organizing this online meeting. Can you see my slides?
Good, I do.
Yeah, perfect. Okay. So this is my talk is going to be a short talk to cover these 2 recent arXiv papers. And the first one is basically a conceptual paper, and it's related to the question that if I give you just a single copy of a wave function, many copies of it, but just for a single parameter, basically many realization of the single parameter, can I probe some many-body features, in particular many-body churn number? Because usually we think of these things that we have a system and we change some parameter and we measure them. Now here we are just facing with a copy for a single parameter, and we would like to see whether that's possible. So that's the subject of the first paper. The subject of and that's the work of my student Zipe and Hossein, who are on the call, hopefully, and my collaborator and colleague at the University of Maryland, Mason Barkeshli. And then the second part of the talk is, once we understand this, can we measure it in a NISQ device? What are the tools that we are available? And that actually was a very nice collaboration with a group of Peter Zoller using randomized measurement. So I hope some of them are online. So this was a collaboration with Peter, Andreas, and Benoit, and also my former postdoc Guan Yu, who's now at IBM. Many of these folks are actually motivated by these ideas. So the main question that we were dealing with was the following: given a quantum simulator within this device, what are the possible and efficient ways to characterize and measure the quantum state? Usually in real material, you're bound to linear response formalism. You shine light, you excite it with some electromagnetic wave, you look at the transverse conductance in the context of quantum Hall effect, and then you measure something. Basically, that's you excite the system, you perturb the system linearly, and then you look at how system evolves. But now we have this quantum simulator. This is a biased collection, depending on my affiliation and collaborations. with ion trap, Rydberg atoms, and superconducting qubits. So the key point here I would like to emphasize is that linear response might not be applicable in some of these devices. For example, we don't have a charge in a bosonic system, so I cannot think of measuring conductance. So what should I do? There are some technical issues, like my system size is small. I don't have disorder to stabilize, and let's say in this specific case, give me these plateaus that we have here. So how can I go about this? The second, which is more important, is that in this quantum simulator, we have access to the full wave function. So we can not only measure the full wave function, but also we can do operations that are not possible in a real material. And that becomes clear in the talk. And of course, we would like to avoid full state tomography, because if you have n qubits and you want to do a full state tomography, you run into an exponential problem. So that's where the word efficient comes from. So in this talk, I will focus actually on the possible rather than the efficient. Efficient is more like the outlook of this stuff. So there are two kinds of protocols, in my opinion. There are protocols that are ancilla-based and they're ancilla-free. So ancilla-based protocols are very powerful because we can do many things with them. So in order to summarize all these ancilla protocols, you can think of it as a very generalized Ramsey spectroscopy. So we have a qubit that is coupled to a many-body state. And then after the Hadamard gate, it goes to two superpositions. In one of the arms, it will experience some Hamiltonian evolution. And in the end, after another Hadamard, we measure the probability, and that gives us some overlap. So this will be, depending on what we choose for H, we can measure some many-body expectation value, or we can actually evolve the system with different Hamiltonian and then look at the properties of H. So depending on how you set it up, you can look into the properties of the psi or the properties of the Hamiltonian. So this is, again, a biased selection of the things that partly I've been involved with, how to use these ancilla-based protocols to do these things. The reason I put it is that there are many of these protocols and they're very powerful, but the experimental implementation of them is very hard. One example is that can we do anionic interferometry? I have an ancilla, depending on its presence or absence, I do a string operator. Or if I have access to the swap, I can not only measure the spectrum of the Hamiltonian, like the one that I just described over here, but the spectrum of a density matrix there that allows us to measure the entanglement spectrum, etc., or out of time order correlators. So these are all ancilla-based protocols. They're very powerful, but as I said, they're experimentally hard to implement. What I would like to talk about here is to do something that is not ancilla-based, it's ancilla-free. So specifically, we would like to extract the many-body Chern number from a single copy on a disk, and then in order to do that, we use topological quantum field theory language. So what I mean, again, by single copy, to be sure that we are talking about the same thing, is that I don't want to change the parameters of the system. I just want to run the same parameters on the device many, many times for the same parameter, generate many copies, but they're all for a single parameter. I don't want to change anything in the system, like the linear response problem. Once we understand this, once we do this conceptual understanding, the second is that can we have a possible experimental realization of it, in particular using a statistical correlation in randomized measurement. And that is an ancilla-free technique. So before moving on, I should first define what I mean by many-body Chern number. So many-body Chern number is defined simply by putting the system on a torus. So I have a two-dimensional system on a periodic boundary condition. It's defined by two twist angles, theta x and theta y. And this wave, and I have a Hamiltonian on this torus. I diagonalize it. I get a bunch of states. They can be degenerate. They can be non-degenerate. But you can think of it as many-body states that are parameterized by two twist angles, theta x and theta y. You can take a derivative with respect to theta x and theta y. That gives you a Berry curvature. You can, that gives you this Berry curvature. So first you would define a Berry connection, and then from there, Berry curvature. You integrate the Berry curvature over all the possible values of this twist angle, theta x and theta y, that itself forms a torus because it's from 0 to 2 pi and 0 to 2 pi in two directions. And in the end, it would give us the Chern number. So if I start with an original state that was a many-body state, I end up with a Chern number that is associated with a many-body system. Now, how it's related to physics in the context of fractional quantum Hall, it is related to the conductance, to the Hall conductance. So C is this integer number that's bound to be integer just by the definition. But now if we have some degeneracy, then we have to divide it by S, the number of degeneracies in the ground state manifold. This is almost always the case, but not always, and I don't get into the details of it, times some fundamental constant E squared over H. Okay, so the examples of it, the famous example is n = 1/3 when the number of particles divided by number of flux is 3. The Chern number is 1, but there are 3-fold degeneracy on this torus. That's give us 1/3 times E squared over H conductance. For hardcore bosons, we can have n = 1/2. Again, C is 1, but since we have 2 states, we get 1/2. So now it turns out that you don't really need to do a full integration over the system if you have access to some parameters that you can vary a little bit. You vary a little bit theta x, and you vary a little bit theta y. Then you measure this. Then you construct this Berry curvature. You can associate the Chern number to that, and up to some correction, this is good. But still, you need to vary this twist angle to have access to the Berry curvature. So the point that we would like to do is that we would like to move away from that. You are doing an experiment. You're just giving a wave function for a single realization of theta x and theta y, and you ask me, okay, what's the many-body Chern number? In order to do that, we have to go back and reduce those 2 parameters first to 1 parameter. That is 1 twist angle. So we have to go back to the Laughlin's argument, how we can get the quantum Hall conductance. This is a transverse Hall conductance. You have to have electric field in one direction and the current in the transverse direction. In order to generate that electric field, you changed some flux in the middle of this annulus from 0 to 2 pi. Because of Faraday effect, it will generate some electric field in the angular direction, and then that will create a current in the radial direction. So insertion of magnetic flux gives you quantum Hall conductance. If you have a neutral system, this current can be associated with the polarization, the derivative of polarization with respect to time. And polarization is nothing but just displacement y in the radial axis. But then if we assume a periodic boundary condition in this direction, in the radial direction, then that's not a good quantity. Then we have to replace this y by y mod L, L being the length of the system in the radial direction. That's where the modern definition of polarization comes about. So to cut the story short is that what REST realized is that instead of measuring the twist effects as in changing the twist effect and measuring the Chern number as in the previous slide, you just need to evaluate this polarization operator. So this was the polarization operator that I just briefly mentioned, and then look at its expectation value for different size when we change this angle phi. Okay, so we take the argument, we take the derivative of this polarization with respect to phi, and that gives us the Chern number. So we reduced the requirement of changing 2 twist angle to 1 twist angle, only one of them. Now, the claim of our paper is that you can actually do even better. You can just give me a single wave function and apply a bunch of operators, and then that would give you the same polarization. And now if you take a derivative with respect to phi, you get your Chern number. So now, since we don't have access to different twist angles, we are simulating the effect of twist angle. We're basically synthesizing that flux threading by this operator W. And then we have this V polarization that we have over here. Extra thing we have to do is that we have to do this swap, partial swap. Again, this is a thing that is only available in our quantum simulators. So the key point that I would like to mention here is that partial swap gives us a non-trivial manifold. So I start with a disk, it will create a torus out of the disk for me. Then second, the application of a bunch of operators V and W gives me the conductance. So this is this short talk. If I've seen TQ50 for the first time, it might be actually a little bit rough here. The idea is that the TQ50 is a theory that is independent of small deformation of space-time metrics. So basically, my observables are insensitive to the small deformations, to the deformations, to the geometry. And then one can have this path integral that then this TQ50 defines a topologically invariant path integral. And in particular, if this manifold has a boundary, then I can associate the boundary with a wave function and it's parameterized on the rim. So an example of it is here, that I have a wave function that is defined at the circle, at the rim of this spherical cap. This would characterize my bra, and this would characterize my ket. So the inner product is just basically gluing these two caps to each other, and then it gives me the overlap of psi with psi, or it can be another psi, like psi prime. That would be given here. Now, instead of gluing them directly, you can do gluing them and reparameterizing it as you wish. This is like contracting matrix product states, but now in space, instead of associating each part to each part, I can do it, I can reparameterize it and then couple the ket indices and bra indices in different ways. So here I would like to identify these guys with these guys, and then double arrows with the double arrows. So pictorially, you have these two eyes that have to be identified. And now you rotate this by pi, so you align the two arrows here and two arrows over here. And then you see that if you identify these two arrows by each other and then one arrow by each other, then you create a handle. And then once you have a handle, if you deform it, you have a torus. So I started with a sphere, I ended up with a torus. So you immediately see that this partial swap can actually change the topology of the system. You're basically synthesizing topology. It's kind of very cool. If you have two copies, and I have one wave function over here, one wave function over here, ket bra, bra ket, bra ket. Now I identify them in the diagonal direction. I go from this over here and then this over here. And if you follow the same rule, then you again make a torus. You don't need to have periodic boundary condition in the x direction. You can just have it open in this one, so you don't have to compactify in the x direction as I have shown over here and as I have shown over here. If you just do these gluing in the way that I just described, you create these handles, and then basically you're locally having a torus over here. So now, what you have non-trivial. I'm sorry.
Sorry to interrupt. We're running a little bit in on time, so I'd suggest taking a minute or two to wrap up, and then there will be time for
I'll wrap up.
Right.
So now, once we have this, actually, we can come up with this seemingly strange and scary formula, but and we numerically test it, and we make sure that this actually formula is correct. And now the second part, which is very brief, is that how to measure this. If we have access to two wave functions, like the experiment at Harvard, Marcus Breiner's lab, one can actually measure the expectation value of swap. But from previous talks in the last incarnation of this NISQ workshops, we learned from Andreas and company that you can actually measure the swap operator by doing randomized measurement. So I don't need to go through the details of it. The only difference with that is that not only we need the swap operation, but also we need to apply some operators before and after that randomized measurement. So to summarize, you just have two copies, two different experiments, you apply some local operators, and then you post-process them, and then there you go and get your Chern number. And then if you numerically do this, then you see that indeed you get your the correct Chern number. So in order to summarize, we extract the Chern number using just a single copy on a disk, possible experimental realization using randomized measurement. And I leave you with the outlook. I think these partial swaps are really cool. We cannot do them in electronic systems, in real material. We can do in these quantum simulators. So I think there is a lot to be done with them. Thank you for your attention.
Excellent. Thank you very much, Mohammad. That's really cool. I think I'm going to go ahead and start the break now. So anybody who wants to take a break, feel free to step away. We're going to start again with the next talk at 9:45 Pacific time. That's in 21 minutes. So the break is formally started, but this is a good opportunity. Any questions for Mohammad? And then we can circle back to any other discussion we'd like. Let's start off if anybody has questions for Mohammad.
There's a question, what machine learning agents we're using? I think this is for the previous talk, right?
That one was for the previous one, yes.
There was no machine learning.
Wait, I'm sorry. I think I walked away for a second and I heard someone say machine learning. Did my question get answered?
Yeah, I think that's your.
Yeah, sorry. This was to the previous speaker.
Yeah. Can you hear me?
Yeah, go ahead, Lucas. Thank you.
Yeah. So we used some ideas from reinforcement learning, but very simplified. So that was something very simple. This basic acceptance rejection based on cost function value with some memory, but nothing too fancy. We're currently actually trying to look into doing this in a more modern way, if you want.
Okay, right. Sounds good.
Did I miss any other question? Let's see.
I think that's covered everything.
Yeah, I don't see anything in the chat.
Yeah, feel free to jump in. This is more informal now. You can also, take a break, get some more coffee, whatever. This is a great moment for that. Another thing we might do is just to make sure. Yes, excellent. Thank you for messaging that, Suguru. If you would, the speakers in the next session, this is a great opportunity to try sharing their slides. So Suguru, why don't you go ahead and try?
Could I ask one question to Mohammad?
Yeah, absolutely. That's a great time.
Like when you do these swaps on a spatially kind of limit, like a small area, right? So does it have to be large compared to the correlation length in order to be quantized?
Good question, and we have some understandings of this. But we don't have the full understanding of it, I have to say. So the naive understanding is indeed the case that the swap operation and also the support of the swap and the support of the symmetry defects is V and W should be larger than the correlation length for sure. Now, when we looked at surprisingly, it worked also for a rectangular system, for an open system. So even when you don't have periodic boundary condition, it works fine. We don't have a good theoretical TQFT understanding of it, but numerically, it works really nice.
I see. Even if you would tune to to somewhere in parameter space where the correlation length is getting long, the quantization remains.
No, for sure. So okay, so the correlation length should be smaller than the support of the system. That's for sure, but that's not the only requirement. So one requirement, for example, would be that these symmetry defects should cross each other.
Yes.
And how they cross each other, we don't have a full understanding of them for an open boundary condition. For a periodic boundary condition, we understand them, and then we go through a whole analysis in the paper, in the long paper, to show where they have to overlap. Basically, the message is that once your V and W overlap, and then you have a large support for the swap, larger than the correlation length, then you get the Cher number. But when we open the boundary condition, when we are in the rectangular geometry, that's not clear.
I see. Thank you.
If Zipe is online and he wants to add something, or Hossein, they should do that. Maybe they left.
Great discussion. Thanks. Just for anybody who stepped away, we're in our break right now. We're going to come back in 15 minutes. So this is an opportunity. Anybody in the second session, I think most of you have tried your slides, but it's a good moment to try that out. And just free discussion if anybody has any questions on the previous talks, or all is well. Lucas, I'm not sure if you're here. We have a question for you, I think, too.
Yes, I'm here.
Ah, good. It's in the chat here, if you can see that.
Oh, I see. Regarding optimization of the space of all algorithms, how did you manage cost function in practice? All right. Yeah. So this optimization is somehow split in two parts. So one is the optimization of structures, meaning meaning discrete parameters, and then of continuous parameters that sit inside some of the gates, right? So the way it works is that you are proposing a small change to your structure, like shuffling a gates a little bit and so on, but then immediately after that you re-optimize all your continuous parameters. Yeah, so because when you only try to update the structure, most likely after that change you will completely destroy your cost function, so it doesn't make sense. You have to follow that by continuous optimization. And then we're comparing cost functions, before and after that update. And then one makes a decision, right? Whether to accept this change in structure, reject, or do something else, or look back in the history, and make some more educated guess, later on. Yeah. So that's the optimization. So we didn't, of course, we didn't look at every single possible structure, that will take forever. We just, try to navigate in this exponentially large space to reach the minimum. Also, another important thing is that, you don't usually have to insist on having absolute global minimum, right? Usually if you are sufficiently low, well, your cost function is sufficiently low, then you are already much, much better than, anything else that was previously proposed. So, yeah, so this is usually helping us out. And this is what I found, that there are many low-lying solutions in terms of a cost function, and any of those solutions, is far better than the textbook plus some simple compilation techniques. And then you were asking also about barren plateau issue. So I think we're not at the scale that would be important. But it's true that once I reach certain size, or I have sufficiently deep circuit or sufficiently many qubits, right, this will show up. We also have some papers on that, and also how to address that issue. And usually those ideas of growing circuits, so you don't want to initialize this with a deep circuit. You want to start with a shallow one, and then gradually grow, and by doing this you introduce more variational parameters, and you further lower down the cost function. So yeah, so this is what would happen, but we haven't tested that. So in practice, it's much more difficult to do that, right? Because I have to run many circuits during this optimization, so I can't actually reach probably the size that this will become a problem. But yeah, we're looking into trying this out and see how this barren plateau problem will come into play and how to avoid it. Thanks for the question. Did you hear all that? I had this weird feeling of talking to a wall. Can anyone hear me actually?
Yes, we can hear you.
Yes.
I would ask a follow-up to that, by the way, Lucas. Like, how long does it take to optimize the agent?
Yeah. So those examples, that I showed, that was like a few hours on a reasonable desktop. So not very long. Well, it depends, how do you think about it? So from my point of view, that was not a long simulation, but that goes well beyond the usual compilation time if you want, right? So I can't imagine that this could be a part of the usual stack, say, at IBM, that's someone submits a circuit, then there is this thing running, right? And then the best circuit or the best compilation or whatever comes out. That takes too long. But yeah, but I think it's if you really want to get the most out of current devices, you really have to allow for this extra time to make sure that your algorithm is as good as it gets for this particular computer. However, when we were working on it, it was clear that we could take some larger building blocks that people typically use in constructing algorithms like this QFT or the overlap, right? And because they show up, in many different places, so one could compile them, right, in a sense, or come up with the really good circuits for that, and then just use them later, right? As they build more complicated algorithms, they could take those simplified versions.
Yeah, thanks, by the way.
Yeah, thanks for the question.
Yeah, I have a follow-up question. I think it's pretty similar. But are you saying we could, say, take some of the building blocks, say like a 3-qubit gate, and instead of trying to implement this exactly, we could use machine learning on these to come up with some approximate circuit that works on this device?
Yeah. I think I didn't hear your question properly. Can you repeat?
So I was just thinking about scalability
right.
problems, and